Well, how are you?
I'm good.
So I think you jinxed me.
Oh?
Yeah, I bought the, when we bought the Switch, I bought the big hard case for it. And in that case comes these little, they're little flaps that you can open up and they hold 4 games in each one. And they're hard cases. You close it down and they stay all nice and neat and I keep them together. And my son lost one of them that has 4 of the games in it.
Oh, no.
Right? One of them is the Ring Fit, which is like $100 game. Right, I use that sometimes to work out in the morning. Yeah, but it's in the case. There's 4 of them in the case, and the case is like, I don't know, it's half the size of a phone. You can't see that, it's blurred, but it's like small. And yesterday I tore this place apart trying to find them. I have no idea where they are. I totally cleaned their room and everything.
I have to keep my SD cards on this bright orange card.
Yeah.
So I won't lose this thing.
It's crazy. I don't know what happened.
I actually did lose this a couple days ago. I was like, I can't find it. How can I lose this bright orange thing? It was under a piece of furniture.
But
at least
I did that.
Once I looked, I was like, oh, there it is, right?
Yep. I don't know.
No, I have
it's like
a whole bunch of these things.
Oh yeah. Yeah, I might have to switch them back to the cases if I ever find it. I don't know what it is. I don't know where it's at.
I don't suppose you can keep backups of those things, can you?
I don't think so. I mean, maybe. I guess you could find something in back. I don't know. I don't know if it's like, you remember the old cassettes? You couldn't do it unless you broke the little tab on the side.
Yeah.
I don't know if it's like that.
I would say it would probably be like some proprietary SD card, right?
Yeah.
It's got an extra little contact on there that's not present on the real one.
Yeah, something like that. Yeah.
I'm sure you could find on eBay or something, some kind of adapter.
Oh, I'm probably, yeah.
Lets you use real SD cards with.
Yeah, plug that in there. So I messed up when you said that I would, and I did, when I was putting stuff into the repositories.
Uh-oh.
So I sent everything into Lab 8. Instead of Lab 9. So you've got, I got to look at the assignments, what they were. Hashing and the lines, the display lines, and all of the files that go along with them.
Oh.
But I shared it with you, so.
All right.
So it's.
Well, we'll get it straightened out.
Okay.
And I realize there's a bit of a learning curve when you're learning how to use version control, and you're going to make mistakes until you kind of figure it all out.
Well, and I was just messed up on what the lab number was. I end up reading the assignments, and I don't really read it. I just kind of skim through it and see what I need to do, and I'm like, all right, cool, let's get it done. And then I start doing it, and I miss those little things, like make sure it goes into 9.1.
And it could have been my fault too. Sometimes I move the assignments around and I eliminate one, or I add an extra one, and I change the lab number here, but I don't change it in the description, or
Oh, maybe, I don't know.
Sometimes that happens.
Yeah.
Oh, how are the rest of you doing?
Doing good.
Oh, doing good.
Good?
Wasn't feeling too good the other day, but now I'm feeling great.
Whoopsie.
It's kind of like my 16-year-old, just about on Sunday, he just suddenly spiked a fever. Almost 103. And, but he's only just now getting a sore throat and a congestion. But for several days, it was just a fever. It's usually kind of the opposite order that happens, right? Usually you get the sore throat first, and then you spike the fever. This was just out of the blue, just suddenly boom. So he's been out of school all week.
Wow.
And then we got a note, and of course you can't go back until you either had the negative test or 10 days have gone by. So yesterday, off to the doctors to get a test. He's like, "Oh, I'm not looking forward to this." They've actually changed the procedure a little bit. They used to, shove that thing way back into your nose. Now they just take a Q-tip and they just run it around the inside of your nose. And he's like, "Oh, that was almost anticlimactic." I said, "Should we go back and demand the old one?"
It was anticlimactic. That's so funny.
And then my other son, we got a note from his school saying that someone in his class that he had close contact with tested positive. So that student's been out all week.
Yeah.
And so now, of course, my younger one is now here, and he can't go back until 10 days have elapsed or he has a negative test.
Yeah.
So we were like, "You're going to get a test." He's like, "No." And then we reported back that all they do is just take a Q-tip now and they just run through your nose. He goes, "Really? Really? You're not kidding?" I said, "No, they're not." "Okay, I'll do it."
Yeah.
Otherwise we were going to do the 10-day thing because it's like this is test number 6 for him. Like every time he gets sick, the school says you got to have a test.
Yeah.
And of course, they've always come back negative because they're just cold.
Yeah. We're fortunate with my daughter's school that they do just a big group testing. If somebody in the class is positive, they just rotate people through to the office and do that just real, invasive nose test with them. But she hasn't gotten sick yet, so that's good. My son's school doesn't do that though. They got somebody sick in his school, so they were like, "Okay, we're shutting the school down for a week. You're at home for a week." So everybody was out. So, but he's 4, so
And in my son's school, they do you got 20-something kids in a class, but they put them into little groups of 3 or 4 or 5 students. So when you go to lunch, you go with your group, right? And so that's probably what happened was someone in their group got sick, and so it only affects the people in their group.
Yeah. Yeah, they do that with their recess at my daughter's school, and they actually draw lines. They take jump ropes, and they stretch out jump ropes to draw lines on the playground. And they say, "You can't cross this line." And so they have to play in their own area. They got 4 sections, and they have to stay in their own area.
Someday this will be over.
Yep. Oh, I can't wait for that day.
Oh, what are we doing today? Okay, we're doing Makefiles for automating your builds and also kind of introducing the next assignment about cracking passwords. All right, so there's actually a video on YouTube that already describes the whole Makefile process. So if you don't get it today, you can watch the other video. It's about 45 minutes long because I walked through the whole thing. But you'll kind of get a version number 2 of that video.
You're saying that's one of your best videos, though, right?
Yeah, that's the most new people. And people comment to say this is the best video on Makefiles they've ever seen.
Nice.
So it's been a while, but we've drawn this diagram how you start with a source file. And then it goes through the preprocessor. And then what is actually the compiler. Then the linker. Oh, not the linker, sorry. Assembler. Then the linker. And then you got your executable. And each one of these stages, you can stop the compilation process at a given stage by passing in a flag to the compiler. Like you can do the preprocessor, I think that was -E. The compiler, you can stop that at -S. Assembler, you can stop that at -c, and then linker, you can't stop that one. Once that one goes, it finishes its job. And so at the end of each one of these stages, you end up with your source file has been transformed in some way into something else. Like after it goes to the preprocessor, it is now, well, devoid of any comments. The defines have been removed and done the search and replace, and the includes have also been removed, and the actual files that you're including have been pasted into your program. So it's been a processed C file, and now it's just raw C code at that point with no preprocessor directives left. What do I call that? I'll just call it processed. And then once it goes through the compilation stage, what comes out the other end is assembly code. And then those files end in .s. Then it goes to the assembler, and what comes out the other end is called object code. Those end in .o. And then those object files then go into the linker where the executable is built. So when you compile a large program, there could be dozens, and in the case of a large application, like a friend of mine works at Google, and he works on the Chrome division, compiling Chrome, the web browser, takes hours to do, because there are just, I would say, thousands, if not hundreds of thousands of files that have to be compiled to put together a large project like that. And so if you are a developer and you want to go and change one file in that whole program, it would be a waste of your time to then start the compilation process over again and recompile everything, because you make one change and then wait for a couple of hours, and then make one change and wait for a couple of hours. That's ridiculous. You only changed one file. So what you want to be able to do is organize the compilations so that if you change one file, you just recompile that one file, and then you link everything together again. And you can go and that's what happens when you go and download a program that you want to compile on your computer, is you just download the source file and then source files, and then they've included this thing called a Makefile that contains the instructions on how to build the whole project from start to finish in such a way that if you make a change to one file, it only has to recompile that one file again. There's a simple one out there that's kind of fun. It's called a figlet. And this is a program that it basically takes any text you type in and turns it into big text using just characters you find on your keyboard. So it's got all these fonts built in. This is the default one right here. It makes text that looks like this, but you can get other fonts that kind of have a fancier look to it. So it's been around for decades, this program, but it's just kind of fun to use. It used to be when you logged into a Linux system, there would be some kind of greeting, welcome to the computer science Linux system. And they would write that in like one of these large fonts. And so they used a program like Figlet in order to generate that. So you can download this, right? You just click on this link. It'll download an archive file to your computer, and then you just unpack it and then compile it. I've already downloaded it. So if we look at our file browser, it is right here. So all I have to do is unpack this and then compile it. And so the tar program is an old Linux program for generating archives of multiple files and putting them together. It's very similar to the zip program on Windows. But it has now created a directory called figlet-225. So let's go into that directory. And actually we can also look at it here. And you can see inside there is a file called Makefile. Let's go ahead and take a look at it. So this Makefile contains the instructions for building the figlet application, the figlet program, along with instructions on how to install it on the system, how to build documentation, how to run tests against it to make sure it's all working. It's basically just a set of instructions on how to build the application. So in order to use it, all we do is we just type make. And then the make program will go and load the instructions out of the make file and then build our application. So, like I said, there's about a dozen or so programs that have to be compiled together. And then at the very, one of the very last steps is to take all of those object files, which you can see here, and link them together to make the executable. So all these steps up here are building the object files, which are being done with passing of the -c flag, and then it then builds the executable out of the object files. And there's actually two executables that it builds. There's another one right down here which gets compiled with -c, and then it links that to make an executable. So there's two programs being built.
What's the difference between Clang and GCC?
Just two different C compilers made by two different sets of authors. GCC's been around a little bit longer, and it was kind of the standard C compiler for many years, and then some other people came along maybe about 10 years ago and said, well, let's make another one, and we've got to give it a different name, we'll call it Clang. It works a bit differently. It still compiles down to assembly and then links to, takes the assembly and turns that into object code and links it together. So the process is the same between them, but what Clang does a little bit differently is it doesn't immediately compile it down to, say, Intel code. It compiles it down to a generic assembly language, an assembly language that's kind of like common to all processors. And then it takes that generic assembly and turns it into the real assembly for the target processor. The idea there is that it's almost like, this is a little bit of prehistory for you, and this may not make any sense to you, but there was a initiative by Microsoft about 15, 20 years ago called .NET. And the idea was you had all these programming languages. You had C and Pascal and C++ and C#, all these languages that people wrote applications in for Microsoft Windows. But they were incompatible with each other, because if you wrote an application in C#, you couldn't use a library that had been written in C, because the way you call functions is just different, and one of them is object-oriented and one of them is not object-oriented, and the naming conventions for things like variables is different. So the code is incompatible, even though they all compile down for, Intel assembly. So the idea behind Microsoft's .NET initiative was to compile down to a generic kind of object format, kind of the same way that Java compiles for the JVM, and then you could have all these languages target this generic assembly code, and then you could link them together to make your final executable. So now it was possible to write, let's say, the GUI in Visual Basic and the background calculations in C or C++, and then link them all together. And
that's the .NET files that we download in Windows occasionally? It'll say you need to download
.NET
this
framework, those things.
Yeah,
That's all the runtime stuff to make that happen.
I've done that a few times, but I never knew what it was. That's neat.
Java kind of does the same thing. There's the Java compiler that compiles down to the JVM, but there are other languages now that compile down to the JVM as well. There's Kotlin, and you can actually get versions of, I think you can get even versions of like C and C++ that compile down to JVM. So the idea is now you can link all those things together and then make one one executable that runs on the Java virtual machine.
So you could write code in C and then compile it and run it in Java.
Yeah.
Well,
I think there's some projects out there to do that. I mean,
but
no one really realistically does that, right?
Yeah.
Why take a fast programming language and make it slower?
Right.
But if you want compatibility,
Yeah. No, that's neat.
So what Clang does is it compiles down to something called LLVM. I don't know what it stands for. LLVM, and that's this generic assembly code. And so you can have different programming languages that target LLVM, and then you can link them together and make an executable.
That's neat.
And so LLVM is itself actually a little compiler that takes the LLVM code and then compiles it. Compile is really a fancy term to mean transform. It transforms it into the target assembly language for that processor that you're going to run on. But you don't have to target assembly language. You could target other languages. So there's this great little project out there called mscriptum that takes C code and it targets LLVM, and then it takes the LLVM code and targets JavaScript. This has been a fantastic project because now every single C program you can write out there can be run in the browser.
Oh yeah, and that's what Thea does, right?
No, that's all written in JavaScript. But
oh, okay.
But there were things like, like old Game Boy emulators and like Nintendo emulators, right? You had to like download the program onto your computer and run it, and ran inside of a little window. But really, the code that runs the emulator is just a C program that emulates the processor and the hardware of that game console. And so now you can take mscriptum and compile it to JavaScript and then run the emulator in your browser.
That's neat. God, I remember doing that. Downloading emulators and
yeah.
Now I think back on it, it's pretty cool.
So that's the big difference between Clang and GCC. Is Clang is this newer compiler that compiles down to LLVM, and then LLVM itself takes over and compiles to the target processor. And what it's meant though is it's made things like cross-compiling a lot easier. Cross-compiling means developing on one platform but targeting a different one. For example, if you want to target the little Arduino boards, right? You can't compile on those things. They don't have enough memory to be able to do that. So you have to use a cross-compiler. You're compiling on your computer, which is like an Intel processor or an ARM processor, but it's generating executables for the AVR processor. That's a cross-compiler because it's targeting a platform that is not the native platform. Is that the long story for the question that someone asked about?
No, that's interesting.
Yeah, that's pretty cool. It really broadens the horizon on perspective for sure.
So I noticed when I was compiling Figlet that there were a whole bunch of these, they're not errors, they're warnings. And I want to go fix those. Now, I researched this last night, so I know what's going on here, but what happened was there is this function called zungetC that is generating this warning. And it's just one function that's being used over and over and over again within the program. And every time it gets used, it generates this warning. So if I fix this one thing, that should fix all of the errors. And so I know that the program or the function in question here is in this file. It's right here. This is actually a define macro. It's inlining a function. So it's creating a function called zungetC that passes in two parameters, a character and a file, and then it just does some manipulations on F and C. And the idea here is, and this is a fancy inline function, is it basically is returning the value of C. But the problem is, if I can find the figlet.c, the problem is, I'm going to zip down to 391, which is where one of the errors is. The problem is that return value is never used. So it just calls zungetC, and the return value is never used, and so this warning is saying, hey, the last thing you're calculating is never used, and so you could actually just get rid of it. So right-hand operand of comma expression has no effect. So if we go into here and just get rid of that last C there and save this, then I'm going to come down here and I'm just going to type make. And you can see the compilation steps are a lot shorter, right? It only has to recompile like 2 files and then link them together and it's done. So imagine if this had been a large project with hundreds of files. I changed one file and then it only has to recompile the files that depend upon that one. Okay? So that's the benefit of the Makefile here, is that it can take your initial compilation, which is a long, involved process, and then any subsequent changes can be made a lot shorter.
Is that define right there similar to like a lambda function in Python?
Oh, I guess. You know, this figlet program being a really old one, dating back several decades, you're going back to a time when compilers were not as sophisticated as they are now as far as optimizing your code, and the processors were not as fast back then. And so it might have made sense for really short functions that you use frequently to suggest to the compiler to inline it, actually to put the code right into the function that's calling it. And so using these define macros was one way to do that, was every time it looks like I'm calling a function, I'm actually just going to swap in this code. So in the call to it right here, it's just going to replace this function call, what looks like a function call, with this code. Just drop it right in. These days,
and that's just for the purpose of saving time when you're coding?
Yeah, saving, not saving time when you're coding, saving time when you're running the program. So it doesn't have to you know, push things onto the stack and create a new stack frame just for the purposes of like running 2 little increments and decrements.
Oh, that makes sense.
Right? So you're getting rid of the overhead of doing the function call.
Yep.
But these days, the compiler is sophisticated enough to go like, well, you got a short little function here. I'm just going to inline the code for you. I'm going to guess that if I actually, and I actually am curious, I want to do this experiment, not today, but maybe after class or something. I want to see, like, if I turn this into an actual proper function whose body is just this.
Couldn't you just do replace all in that?
So actually,
drop it in.
So instead of having a define, actually make a function called z_ungetC.
Oh,
that passes in 2 parameters and returns, you know, an integer.
Yeah.
And then this is the body of the function.
I see.
First of all, certainly the warnings will go away. And secondly, I'll bet you the code is not any different.
Probably.
The compiler will just inline the function for me because it sees it's nice and short. But that's beside the point, right? So the point was, I changed one file and then the compilation process was a lot shorter because there was only a few files that had to be recompiled. Okay, so let's take a look at how we would compile that program that we wrote last time. That was the brute force program. Remember this one?
Mm-hmm.
So what did we type in to compile that? We typed in Clang.
Yeah, Clang brute force.
Brute force.c.
And then
md5.c.
md5.c -o brute force -l crypto.
So that's a fair amount of typing to do every time you want to compile. Now, of course, you could just hit the up arrow key and just repeat that command again. But if you had to do it like from scratch every single time, that's a lot of typing. You could put that into a shell script. You know, we could actually literally do that. Let's copy this, create a new file. I don't know, let's call it build. Paste that in, turn it into a proper shell script. Save it, and then what do I have to do to make this build script runnable?
Change the permission first, and then now you just
Right? And behind the scenes, it ran my compile command, and so you could do that. But it has the one shortcoming that every time I compile my project, it's compiling everything from scratch. It's compiling bruteforce.c from scratch. Whoops, didn't want to scroll that. It's compiling bruteforce.c from scratch, md5.c.scratch, building executable, and linking in the crypto library. But if I only change one of those files, like if I only change the bruteforce.c file, I shouldn't really have to recompile md5.c because I already compiled it and it didn't change.
Mm-hmm.
So let's see, I've got two source files. I've got bruteforce.c and I've got md5.c. And then what I can do, instead of compiling them all together, is I can compile them separately. So I want to build the object files for these. And the command I would use to build the object file from the C file would be Clang-C bruteforce.c. And the command I would use to build md5.o out of md5.c would be Clang-C md5.c. So let's try that over here. So at this point, I've now got two object files. I've got bruteforce.o, and then way down here, I've got md5.o. Those are the two object files that make up my program. And then now I want to link those together and build my executable. So you're looking at this going like, command line's not any shorter, right? But this third command has taken my two object files, built the executable, and linked in the crypto library at the same time. So let's go back over here. So the command I did to bring all this stuff together was Clang bruteforce.o md5.o -o bruteforce-l crypto. Okay, so 3 steps to compile this program. Compile bruteforce.c into its object file, compile md5.c into its object file, and then link those two object files together and bring in the libcrypto that we also need and make the executable. Okay, it seems like a lot of work to compile one small program, and for a small program it probably is, but I'm using this as a way to illustrate how to write a Makefile. What we're going to do is write out the instructions for building this project in the Makefile. And you know what? What I'm really going to need to do is I'm going to have to put all this into a directory, because I might have more than one Makefile. I might have a Makefile for lab number 10 and a Makefile for this example, and so I can't have the same Makefile for everything. So let me go ahead and just make a new folder. Let's call this brute force. Oh, I already have a file called brute force.
You still got the whiteboard.
Oh, thanks. Let's call this, let's just call it BF. Let's just call it brute. Let's just call it brute. And let me put all the stuff in there. Put that in there. Oh no, I can't drag that over. It doesn't scroll. I'll have to do it by hand. Okay, now I've got everything in there. Okay, so here's what the Makefile is going to look like. New file. First of all, it has to be called Makefile with a capital M. So I'm going to show you what goes inside the Makefile, and then I'll explain what it all means. Okay, so every what's called recipe in a Makefile consists of 3 parts. There's a target, a dependency, or it's also called a prerequisite, and then an action. So the target here is the executable called brute force, and the prerequisites are that bruteforce.o and md5.o exist. And then the action to build the target out of the prerequisites is this line here. And then I got 2 more recipes. The target is bruteforce.o and its dependency is bruteforce.c. And here's the action to build bruteforce.o out of bruteforce.c. And then finally a similar thing for MD5. And so what this Makefile does is it encompasses this tree that we built. In order to build bruteforce.o, or brute force the executable, these 2 object files must exist. And if they don't exist, the way to build this object file out of the source file is to run this command. So it's a dependency tree, and it will only run the commands it needs to. So if I change the bruteforce.c file, it will then rerun this command, build the object file, and then relink it together. If nothing has changed, it won't do anything. Okay, so let me save that. Let me remove those .o files. I have to be very careful.
Can we see that Makefile again?
Oh yeah. Now, on line 2 and 5 and 8, I hit tab to go over. It's very important to put a tab there. If you use 4 spaces, it will not work. So here's what a recipe looks like. You've got your target, a list of prerequisites, and then a tab, and then your actions. And you can actually, there could be more than one action. Like if you have to do 2 or 3 compilation steps to build that target out of those prerequisites, you just list them on subsequent lines.
Is there any way to put a note on this Makefile because the // isn't working?
Oh, hash mark. Okay, so I'm going to save it. I'm going to type make after removing my object files and executables, so I got kind of a clean slate. I'm going to type make. Uh-oh, I didn't include my md5.h file in there. Let me just quickly copy it in here. There we go. Now, let me type make, and you can see it did those 3 commands. It compiled bruteforce.c and built bruteforce.o. It compiled md5.c and built md5.o, and then it took those object files and linked them together to build my executable. So now if I go and change something about my bruteforce.c file, let's take out this commented code that we discovered we could just rewrite in 1 line. Let's take this out. I'm going to save my program, and now when I type make, it doesn't have to recompile md5.c because I didn't change that one. It only recompiled bruteforce.c and then linked them together at the end. Okay, last thing about the Makefile is you want to construct the Makefile with the thing that you're targeting up towards the top and then the dependencies down below. So it's kind of like you take the tree that we built over here and you have to turn it upside down. So this would be the first rule that you write, and then you write these other rules down below it.
Quick question, why does mine say that it can't find the directory? When I ran it, it said no such file or directory.
So did you make a directory for your?
I have everything in the directory CP file.
Mm-hmm.
And when I ran it,
and your shell is in that directory.
Yes, but it doesn't file. I deleted the .os,
mm-hmm.
and then I went to compile it, and it says that it can't find the .os.
Did you delete the executable also?
I did star.o, possibly. Nope, that's there.
So when you start out, you should have only...
See, now it created the O's, but then it said that it can't find them. I don't know, that's weird.
Check for spelling errors?
Oh, yep. Oh, man. I'm so used to camel case that I do that and then I end up not. Wow.
John says that happens to you all the time. Happens to him all the time.
Oh yeah, same here.
That's one of the big differences in some of the languages, just the naming convention.
Yeah.
In C, the naming convention is all lowercase letters. And
actually
the old style was all lowercase letters, and if you had multiple words, you connected them with underscores.
Okay, I thought it was camel case for everything.
with the influence of Java and C++, you're starting to see more C programs written with camel case.
Yeah.
But for years and years, it was words with underscores between them.
Okay.
Or, better yet, or worse yet, words shortened, like vowels have been discarded. And,
yeah.
Yeah. Because C is an old language, and you used to run C on the old teletypes with the typewriters. And so the more verbose your program was, the longer it took to print out and the longer it took to type.
Yeah.
So you kind of wanted to make things as short as possible. So you see really old C programs have short, almost cryptic function names. They can just barely be pronounced.
Like that could mean 5 different words. What is it?
Okay, so that's the basics of a Makefile. It is a way of representing from top down this dependency tree that I drew on the iPad. So when you type in make, it looks for the very first recipe and then starts building the program from there. It checks to see, do these .o files exist? If they don't exist, then before it executes this action, it'll go and find recipes for building those files and then execute those first. So it kind of walks its way up that dependency tree and then walks its way back down. And you can have really deep dependency trees, or you can have really wide ones, or you can have ones that go into multiple directories if you have lots of files to build. Now, sometimes it's also helpful to have some other recipes in there for the purposes of running your program. Like, I can make a target called, let's say, test. And it depends upon the brute force executable being in existence. But inside a test, all I'm going to do is write the commands to run the program. I could say /brute force, and then a hash that we want to crack. Now I don't remember one, so I'm going to have to find one. Let's see. MD5 display as bytes. Grouping together, and then what word should we try to crack?
You could do about. Are you going to use the one that you made yesterday?
Pizza.
You could use pizza.
Let me save that. And now what I'm going to do is I'm going to type in make, and then I can put the name of a target. So I'm going to put in make test, and now it's going to jump straight down to that target and run that command. Found pizza. So this is great because now I don't have to go and look up that hash every single time. I can just put that in my Makefile, and now I've got a built-in, ready-to-go way to run my program. I could even do something like, I could call this pizza, right? Make pizza. And then I could put in hello here.
If you run the make command without specifying test or pizza or hello in this case, will it run each one of those?
No, it just starts with the first rule and goes from there.
No, I mean like when when it gets down to pizza, will it run?
No. So
because I just typed in just make, and oh wait, no, yeah, just make test, and then did that one.
Yeah.
So it won't do all of them, right?
Right. There's nothing in this. When you just type in make without any argument, it just looks for the first rule and runs that one.
Okay.
And there's nothing in the tree that's built up by this rule that references pizza or hello. So these are kind of standalone ones.
Okay.
So now I can go make pizza, and it will run the program searching for pizza. And I can type make hello, and it will run the program looking for hello.
Nice.
You know, I could even do stuff like this. So now when I type make test, it'll just go ahead and run make hello and then make pizza.
Oh, that's cool.
And then run all my tests. Actually, I think I could do that differently. That's one way to do it. I can also do it like this. So what this rule says is that if I invoke the test target, it'll try to see if the hello file exists. Well, it doesn't exist. I don't have a file called hello. So then it goes over to this this target, and then runs this command in an attempt to build the hello file. One never gets created, but that's okay. And then it will invoke the pizza target. It'll try to run this command in a desperate attempt to try to build the pizza file. But none ever gets built. So when I run make test again, it just reruns everything.
So wait, does it also run the first one in the list where it tries to create the executable out of all the object files?
Well, yeah. So let's remove the object files and my executable, and now let's run my tests. So what do you think is going to happen when I run the tests here?
It's probably going to try to make it again and then run the test, right?
Yep. So it's going to build everything and then run the tests.
Nice.
So what happens there is I invoke the test target. It tries to run the hello target. It goes up to the hello target. It sees that the brute force executable does not exist. So it comes up to this rule, looks for the .o files, sees that those don't exist, comes down to those rules, builds those, and then works its way back up the tree.
I'm still having issues with the start of this. It's saying that the command's not found. I named mine originally crack pass. And yeah, it says line 2 crack pass command not found. Which is, I mean, it's written exactly the same.
And you're using a tab here?
Yep.
And another thing to check is, down here at the bottom of the screen, this is where you can select what kind of file this is. Does it say Makefile there?
Yes, it does.
Okay. What that does is it knows what kind of file you're editing. And so if you're editing a C file, you can see this has changed to C.
Oh, I see.
Then when you
okay.
then it does things like the auto indent, and when you hit tab, it replaces them with spaces.
Okay.
But when you're editing a Makefile, it's very important that the tabs actually go into the file as a tab, not as a bunch of spaces.
Gotcha.
I read an interview with the person who originally wrote the Make program. He said that's the one thing he regretted.
Oh, really?
Was not making the spaces and the tabs be equivalent to each other. Back then, it had to be one tab and exactly one tab, is what it was looking for, to know whether this was the start of a recipe or an action. It was looking for that tab. And ever since then, developers have cursed him, right? Because it's like, why can't I use a space there? And he says, why can't we change Make so that it accepts both spaces or tabs? And he says, well, now it's too late. There's Makefiles out there that have spaces because they intended to be spaces and they're not intended to be tabs. And it would break things. So that's why it has to know what kind of file you're editing, so in order to know how to treat the lines of the file, and also to do syntax highlighting correctly, right? The targets get turned into kind of like this brownish color, the comments are green, and for C files, again, comments are green, but names of functions are like blue,
Mm-hmm.
Right, so different coloring. So you're still having a problem with yours?
Yeah, it just it says that it can't find the command.
What command?
Crack pass.
And
So like yours is brute force on line 2, mine's crack pass. And I run it and it says line 2 crack pass : command not found.
And
then Clang error, no such file directory crackpass.o.
You're doing Clang here, right?
Yep. Clang crackpass.o md5.o -o crackpass.
Do you want to paste
L
your
crypto.
Want to paste your Makefile into the chat?
Sure.
Did you add the / on the lower ones?
I think you
Yeah, check your spelling.
Yeah, check your spelling.
Oh shit. Oh my god. It's embarrassing.
Oh, nice.
Okay, it still says that it cannot find it. That the command's not found. I changed that one and then I did a change all on the other ones. So just assume that terrible thing is
And what's
spelled correctly.
Can you paste in the error message you're getting?
Yep.
Oh, you're trying to run this as a script.
Oh, do I need to?
You just type the word make.
Oh. Wow. I thought it was a script.
No, it's not a script.
Okay.
Well, it's not a script in the sense that it's not a shell script.
Yeah, I'm like
Yeah.
going back and forth from 50 to this and
So you're running the make program.
okay.
And the make program loads the make file in.
I see. And it worked. Like
And then
a charm.
someone on YouTube pointed out
Wow.
that for these targets here that don't actually generate any files, you really should put in, I think it's .phony pizza and .phony hello and .phony test. That just lets make know that let's make note that no files will actually get generated. And
Are you the person from YouTube that said that?
no. Okay, so I'm going to add one more target to this Makefile, and then we're done with Makefiles. And that is, I'm going to make one called clean. And this is a pretty standard one to put in. Again, it's a phony target, doesn't generate any files. And the whole purpose of this clean target is to remove all of the artifacts of compilation so that you're left with just your source files. And I usually pass in the -f flag so that it doesn't complain if these files don't exist.
What's the difference between RF and F?
Okay, so F means force, and basically it means don't complain if the files don't exist.
Mm-hmm.
And the R means recursively go through all subdirectories and remove the contents of those directories as well. Well, we don't have any subdirectories, so we don't have to do that.
Okay.
So now if I type in, and double check this, no extra spaces in here like, I would have done if I was doing this at 4 a.m. Now I can just type make clean, and it'll remove all of the compilation artifacts, and I'm left with just my raw source files. So you really only have to do a make clean if you have a bona fide reason for like removing everything and cleaning the whole thing up. Like maybe you're getting ready to package it all up so that you can send it to someone else. Right? You don't want to have all the compilation stuff in there. It's extra space. They're going to rebuild it themselves. And besides, they might be building on a different architecture, and those executable files just wouldn't run in the first place. So you can do a make clean before you're getting ready to package it all up. There's really otherwise no reason to run that. I know a lot of students, what they do is they go make clean and then make test, right? Every time they clean up all their files and they run make test, right? It doesn't add a whole lot of time to your compilation because the programs we're compiling are pretty small. But if this was like Google Chrome, I would not write make clean before I ran my make file again, right? Because that would not just be something I would do all the time. I would do that if I wanted to make absolutely sure that I can do a clean compile from start to finish, like before I check in my code or before I give it to someone else. But as I'm doing my development, of course, I would not do a make clean before I did a compilation. Okay, so that's enough with Makefiles here. I mean, of course, you can go. There's a book on Makefiles you can get. It's this big, giant, inch-thick book you can get that has all the stuff you can do with Makefiles. You can write patterns that do automatic compilation, so it can look for any .c file and turn it into a corresponding .o file by writing one recipe. I'm not going to get into that. You can look up how to do that. You can do recursive makes that go into subdirectories and build everything in subdirectories and then come out of those directories. Right? So there's a whole bunch of stuff you can do with Makefiles that I'm not covering today, but this is the basics. Is you start with this diagram of how your program is built, and then you turn that into the Makefile that basically encompasses all of that, all those instructions. So what I want to do now is we want to write a program, like we have one now that brute forces the password cracking by trying every 5-letter word. But instead, I want to write one that uses a dictionary. Okay, so I got a dictionary of possible words that it could be, and then I'm going to try all of those. So I guess the first thing we should do is, well, let's see. How should I do this here? I didn't plan this far ahead. Should I use a pre-built dictionary, or should we just write our own dictionary? I don't know. I guess I'll use a pre-built one here. So I'm going to go and just fetch one here that I've got.
Say if I have to type it out, chances are there's going to be something pretty terrible.
Here's one. So let's put in a new file here. Let's call this that's a terrible word. Just call it words. Let's just call it words. I knew that was going to happen, man.
Look what you've started, Terry.
I know.
This is an adults only class, right? You know, no, I'm not going to bring that up. Okay, so I've got this dictionary of words, and so this comes from a file called RockU, which is a file you can download off the internet. It's about how big is it? 14 megabytes packed, and then when you unpack it, it's about 140 megabytes of known to be good passwords that have been leaked out of password database leaks. This is back from 2009, so it's shorter than it would be today, but it still is a great starting point for possible words you could try if you want to crack someone's password, because chances are the password they're using comes out of this list. It's just a list of like the 14 million or so most common passwords. And it turns out the most common password is 123456. It still is today, some variation on that. Password itself is number 4. You still have like I love you as a common password. And researchers have recompiled this list pretty much every year since 2009. And the top 10 basically doesn't change. People are still using the same dumb passwords 20 years later, 10 years later. Now, I've gone through this list and removed the, more scandalous ones. But, basically, it's a list of the top 100 or so most popular passwords. So what I want to do is write a program that's going to attempt to crack a hash by using this dictionary to actually use as my candidate word. So instead of trying every possible 5-letter word, I'm going to use all the words in this dictionary. So what we need to do is actually take one of these words, hash it, and then we're going to try to crack that. So which one should we pick?
Whatever.
Whatever. Is that in there? There.
Right there.
Whatever. Whatever. Okay, so this is the hash we're going to try to crack. What am I doing? Oh. So I guess in the interest of some time, I'm just going to build this program right inside of this directory that I've got here. I'm going to call it something else. So let's call this program Brack. No. Crack word. And the nice thing about putting it in the same directory is I can recycle that pre-built MD5.0 file. And then I just need a rule to build crack word.o out of crack word.c. Okay, so let's build that program. Oh, by the way, if you want these MD5.c and MD5.h files, because you're following along but you don't have access to the files, I made a Bitbucket repository which you can use. You just go to bitbucket.org/csci46/MD5. You can forget this source and master, right? Just this portion of it. And that should drop you into a place where you can download these files. Here, I'll see if I can put that link into the chat. I don't know if it'll accept it, but we'll try. There we go. Okay, so I want this program to run so that I can just put the hash in on the command line, and then it's going to use that words.txt file to crack it. So let's do kind of the same thing we did before, which is character pointer hash target hash equals argv1. Oh, first thing we should do is check to make sure they got enough parameters on here. So if argc is less than 1, usage, %s, and then hash to crack. So if they don't supply a hash to crack, it's going to print out this error message, and it's going to swap in there, in where this %s is, the name of the program. It's kind of neat, because now I don't have to know what the name of the program is. It will just drop it right in there.
And that's the arg0 that does that?
Yeah. So argv0 is the name of the program itself. Okay, so to be able to crack this hash, I now need to open up the dictionary file for reading, read it one line at a time, hash each one of those words, compare it against the target, and if they match, I found it. So we're going to open it for reading. Let's check to make sure we actually opened it. If we can't open it, we'll print out an error message along with the reason why we couldn't open it, and then we'll exit the program. Okay, so now we got it open. We're going to start reading that file in one line at a time. So we'll use while. Oh, we need a string. So let's go character word. And if we look through that file, we can see that all of them are pretty short. Right? Nothing here that's maybe more than 10 characters or so. So this is our standard using fgetS to read one line at a time out of the file. Now we're going to get the word out of the file, but the word is going to come with a new line character on there. So we got to get rid of it. Remember how to do that?
Yeah. Make the new line string plain new line, or I guess it would be not plain, but yeah.
And what function do I use to find that?
String compare.
No? Almost.
String character.
String character, yeah.
Yeah, that's right.
Oh, someone pointed out I forgot to put on line 19 standard error in front. I always forget that. Okay, now if there is actually a new line character, then go ahead and replace it with the null. Okay, I've got myself a word. I've got myself a target hash. I need to hash the word and then see if the resulting hash matches my target. How do I hash that word?
Create a new array and then call the MD5 and put
so I don't need to make a whole new array, because MD5 function is going to return to me the string with the characters already in an array. So all I need is a character pointer.
Oh, okay, I see. I was mistaking that for an array. Okay.
So, well, let's be specific. It is going to be an array, but I don't have to create it.
Right. That just stores it in a different spot in memory, right?
Yeah.
And then it doesn't get changed.
Next, we're going to check to see if that hash that we just calculated matches our target hash. We'll use string compare for that. So if it does match, we found it. So I'm going to print out the hash along with the target word that we found. And then at that point, we're pretty much done, right?
What's the difference between exit 1 and exit 0?
So When your program exits, it sends back to the shell a number that indicates how well that program worked. And the convention is 0 means everything's good, and anything other than 0 means something went wrong.
Gotcha. Okay. That's cool.
That way your shell script, or your shell, if you're writing a script, let's say to call this program, it can learn, or not learn, it can obtain information about whether the program worked or not. And it itself might generate an error message.
Okay.
So it can look at the return value. If it's equal to 0, then it knows everything was good. If it's something in return other than 0, it can then print out its own error message.
And you could essentially list all of the exits in different orders, and then you could tell where.
Yeah. So I could like assign the number 1 to mean didn't use the program correctly, and number 2 means couldn't open the file.
Yeah.
Number 3 means couldn't find the hash, right? And you would document all that. These are what the return code, the exit values mean.
That's neat.
In fact, we could do that if you wanted. Right?
We're still looking at your face.
Oh. So 0 means, hey, we found it, right? Everything went good. If we get all the way through the loop and we never find the hash, we could then exit with maybe 3 to indicate that we never found it.
Okay.
Maybe we'll also print out a message. Okay, so I think we got our program. Let's go ahead and...
Oh, are we going to add any of the malloc frees? Like where we free the memory?
Oh, that's a good point. So every time we call MD5, there's a malloc that happens behind the scenes. So we're going to have to free up that memory because we're doing a whole bunch of hashes, right? We're going to be doing 100 hashes. So we're going to end up with 100 chunks of memory that get allocated. Where should we do a free?
After the if statement, if we find it. Like after those brackets, though.
Down here?
I think so, yeah.
And one below the printf inside the if statement.
In here? Okay.
Yeah.
Okay, so let's type make crack word. Now I have to put the name of the target on because without the name of the target, it's going to look for the first one. And I don't want the first one. I want the second one. There, it built it. It didn't have to compile md5.c because I already had that one compiled. So now let's run it. Crack word. And then here's the one I'm going to crack. Copy. And there it is. It found it.
That's neat.
That was super fast, right? Because I'm not trying millions of possible words. I'm only trying about 100 of them. Let's try a different one. Let's do this very last one. Found it. So we could put these into my Makefile. Then I can change my test target to not do hello and pizza. You can do whatever and Alexandra. It just runs them. Test my program out.
Could you explain why you added brute force to the right after Alexander and whatever?
Because I mistyped it. Is that better?
Yeah. I was confused for a second.
To be able to run this test, this crack word executable has to exist. Okay, so let's go back and look at our program. So first we check to make sure they typed in at least one command line argument. If they didn't, print out an error message. Then open the file for reading. If the file couldn't be opened, print out an error message. Read it one line at a time. Strip off the new line. Hash the word. If it matches our target, then print out we found it and exit with a code of 0. And then if we couldn't find it, exit with a code of 3. So if we run our program and we say echo $? We can find out that this returned a status code of 0 because it found it. And then let's go ahead and put in a hash that it's not going to find, like Alexander with an exclamation mark. We can see it returned a status code of 3. Okay, so the last thing I want to do before we take a break is let's run this under Valgrind and see what it says. Let's just take one of my ones that work, and we'll put Valgrind in front of it. Okay, so it says that in use at exit, there were 472 bytes in one malloc. We didn't lose anything, we didn't leak anything, but there was still some memory in use at the end. It says rerun with -- leak check equals full to see details of leaked memory. We don't, let's try it out. Let's run it with this option, see what it says. Didn't give us anything different, so that didn't help. And normally it might, but in this case it didn't. So where are these 472 bytes coming from? So when I look at a message like this, I go, okay, let me think about all the mallocs that my program did. So in MD5, it does a malloc of 33 bytes because we need space for the hash plus the null character. So those are 33. And this number, 472, is not a multiple of 33. And in fact, it only comes from one malloc. So it doesn't come from anything from MD5. Where could this come from? Any ideas?
Is it from the file structure?
Yes. That is it. We opened the file here.
Oh, and they didn't close it.
But we didn't close it. So fopen allocates some memory to hold information about the file, but then we didn't close it. So right before we exit, we have to fclose W. And then right before we exit here, we need to do an fclose W alt as well. Let's see if that fixed the problem. Oh, I need to recompile it. That did. That fixed it. So that was the problem. Okay, let's take about a 10-minute break, and then we'll come back and look at the assignment for this week.
Recording stopped.
Okay, we're back from our break. Someone pointed out that if you run the program without any arguments at all, it crashes. And I tried it out, and sure enough, that's what it does. So we have a bug in the program. And we did put in a test to see if the number of arguments, we checked the number of arguments, but apparently this test failed. So what's going on? So this should actually be 2. The only time that argc is going to be less than 1 is like never. Right? It's always going to be at least 1 because there's always going to be the name of the program. So this should have been less than 2.
Yeah.
Oh, my son has brought me a package. What do we got here? Oh. Medicine for my dog. All right, so less than 2. So let's try doing make crack word. And then let's try running it with no arguments. And now we get the correct error message. And then just to make sure that it's in fact working, let's try to run it with an argument. That we didn't break that. Good. So it says it couldn't crack that because that's the one that we don't have a solution for. And then this one works good. So fixing that bug didn't break the program. All right, so let's go and look at the assignment. So in this program, you're going to be writing a program to crack hashes, but it's not just going to be one single hash like we just wrote. It's going to be to crack a file of hashes. You're still going to be using a dictionary, just like we did, but it's not going to be one single hash. It's going to be like 10 or 20 of them. So to start out this project, go to my repository. Just click on this link here. It'll open up in a separate window. And then you're going to make a copy of this repository. So I think, is it under the plus? Yeah. So you click on the plus over here. And then click on fork. And that's going to make a copy of my repository into your account. That way, when you make changes to it and push the changes up, they're going to go to your repository, not mine, which you don't have any permissions to change. Okay, so just to redo that again, you click on this plus, go down to fork this repository, and then it will make a copy of my repository into your account. I think it'll prompt you to give it a name. Just keep it the same name. Once you've done that, you are then going to clone your copy of the repository into your development environment. So there you click on this clone button, which on mine is over here on the right-hand side. If you can't find it over there, then maybe it's under this ... menu. Oh, there's also a forked repository there as well. So you can do fork there. If you can't find the clone there, then who knows, maybe it's over here as well. Oh, there it is, look at that, clone this repository. There's a bunch of ways to get to that. And then it'll give you a command that you're going to copy. Then come over to your development environment. And then here's an important step. Make sure you're back in your home directory. Don't clone it into your brute force directory that we've been just working on. So to make sure you're in your home directory, you can just type cd by itself, and that'll move you back into your home directory. Alternatively, you could close the terminal window and open a new one. That'll put you back in your home directory.
pwd will tell you where you're at too.
Yeah, pwd tells you are in your home directory. And then we're going to paste in that command. So again, you're going to fork the repository. That makes a copy into your own account. And then you're going to clone your own repository. Don't clone mine, clone yours. And you'll know that it's the correct one because when you copy in or paste in that clone command, it'll have your name here, right? This is my name. It'll have your name here in front of the @ sign. And it should also have your name over here. So just make sure it's your name. And now you've got this directory called crack2 that contains all the starter files for this project. Now here's where I suggest you might want to open a separate workspace. Oh, I need to go and re-authenticate myself first, so let me do that. There we go. That should take care of it. So by opening a separate workspace, I now have isolated the files just for this project. And when I open a new terminal, it'll already be in the correct directory. All right, so let's take a look at the assignment. So we've obtained the starter files. We're now going to create the file of hashes. So it says, run this command, make hashes. Let's go ahead and do that. Going to compile a program and then run some other commands, and I now have a file called hashes.txt that contains the hashes you're going to be cracking. Those are 20 randomly picked words out of the words file that got hashed and then put into this file. So you can see what here's what it did is it compiled this program called hashpath, which is very similar to the one we wrote last week, right? That just hashes a single word. And then it shuffled the rocku100 file, picked off the top 20 words, and then put those into a file called passwords.txt. So you can actually see what the answers are over here. These are the 20 words that it picked. And then it ran that hashpath program using the passwords.txt program as input and outputted it to hashes.txt. And that's what you see here. And your goal is to write a program to crack all of these hashes. Let's take a look at the Makefile. At the top of the Makefile, there is a number that you can change, which is the number of hashes that you want to randomly pick. By default, it's 20. You could change it to 100 or 50. And you can also pick which rocku file you want to use. By default, it's using the rocku100 file that contains the top 100 most common passwords. But you could pick the one that has 1,000 or 2,000 or even 1,000,000 words in it. All you have to do is just put a comment symbol in front of the one you don't want to use, and then remove the comment symbol in front of the one you do want to use. And then we can just build a new set of hashes. Okay, so inside there are some targets and recipes for building that hashpath program. Don't have to change anything there, but there are a couple of places for you to put in some actions for building the crack program. I love this part of the semester, right? Because we go through, say things like make crack, make hash, right? People look at us like we're a little...
Forget to put the P in.
Yeah, people look at us like a little weird, right? So what you need to do here is replace lines 29 and 30 and 36 and 37 with a compile command that will build the executable out of these two object files, and also to build this object file out of the C file, and that's it. So there's two rules to put in there. Then you'll be able to type in make, just make, yeah, make, and it will build your entire project. Okay, once you type in make, it'll build the template programs. They should compile, but they won't do anything. Hello, Cat. Cat has come in to see what all the hubbub's about. Yeah, I'm not talking to you. All right, so now all you have to do is edit the crack.c file. You don't have to modify any other programs. Let's take a look at that. So there's a main. The main, there's going to be two files passed in as command line arguments. One is the hash file that contains the hashes you want to crack, and the other is the name of the dictionary file. So your main needs to open the hash file for reading, and then read each line of the hash one at a time, and then pass it to a function called crackhash. Crackhash will return to you the string that contains the cracked password. Right? So you pass it the hash that you want to crack, and then it passes back the actual thing that it found. And then close the hash file, and then if there's any malloc memory that you have to clean up, then this is the time to do it. And then up here in crackhash, you're passed in the hash that you want to crack, along with the file name for the dictionary. You're going to open the dictionary, loop through it one line at a time, hash each password, compare it to the target hash. If they match, return the corresponding password, and then finally close the dictionary file, free up any memory, and then if you weren't able to crack it, you're going to return a null. So you probably figured out by now this crackhash function is going to look very similar to the program we wrote half an hour ago. Okay, and then that's the program you have to write. So you can try it out with those different Rocky files. You'll find that it works pretty quickly for the Rocky 100 and the 1000 and the 2000, but then you throw at it the 1 million file, and then it starts to slow down, right? Because there's just tons of passwords to hash, right? So for every hash that you want to crack, it has to open up that dictionary file, and it has to read in all 1 million words, right? Hashing each one as it goes. When it finally finds the one that matches, it's done, and it moves on to the next one. And then open the file again, read the whole thing in, right? So you're just hashing the same 1 million passwords over and over and over again. That's what slows it down. So what we're going to do next week is how can we speed that up? And there's two ways we can speed it up. One is, instead of loading the dictionary in every single time, why don't we load it all at once? Then we're not
do that in the Makefile?
No, I mean like in our program. Load the dictionary into a giant array.
Oh, I see.
And then we can just read out of the array over and over again. That'll speed things up because now we're not reading off of the disk every single time, reading out of an array. And then the other thing we're going to do is build a data structure so that we can search through that dictionary really fast. And that'll speed things up as well. Okay, so that's your assignment.
It's going to be fun.
Yeah. Lots of Valgrind, right? Run that. There's actually a target in the Makefile specifically to do that. If you type in make check.
Yep, right there.
Right there at the bottom. Then it will run your program. generate that report for you.
Cool. Yeah, those Makefiles are super convenient.
Oh yeah. And there are some more contemporary replacements for it. There's Ant, which is primarily used for Java programs, but could be used to build anything.
Did you say and?
Ant.
Oh, ant.
Ant, like the little
yeah.
insect.
Okay.
And then there's like Maven, I think, again for Java programs primarily. But Makefiles are easy to understand and still used quite a bit with C programs. In fact, when you download a large project from the internet, where it doesn't even know what kind of system you're running on. Are you running on a Linux system? Are you running on a Mac? Are you running on Windows? Are you running on some of the older Unix systems like BSD or Next? It doesn't know, and so things like include files might be different. The libraries you need to link with might be different. And so there may in fact be a step you have to do before you run make. Sometimes it's called configure. So you run this script called configure. So you go /configure, and then it goes through and it takes inventory of what it sees on your system. It learns the name of your compiler by trying to compile a small program and see which one actually generates an executable. So tries GCC and Clang and CC and a whole bunch of others. And the first one that works, it goes, oh, that's the name of the C compiler. And then it tries to build programs to link in the libraries it needs in order to learn what the name of the library is. So it might try crypto, it might try SSL, it might try a whole bunch of other things. And so the purpose of this configure script is to write the Makefile.
That's cool.
And then once that configure is done, it takes about 2 or 3 minutes to run and try all this different stuff to learn about your system. And then it builds the Makefile, and then you type make. And then it goes through and compiles the program.
That's neat.
And there's another one called CMake that kind of does the same thing. You include with a CMake file, and then its purpose is to build the Makefile. Again, learning about dependencies on your system. What resources
C for
available.
configure.
Yeah.
That's neat.
So back when I was compiling large programs, you just learned this incantation: configure, make install.
Yeah.
Configure to build the Makefile, make to build the program, and then make install for it to go and actually copy the parts into the various directories that are needed on a Unix system. Because that was back in the day when there weren't package managers for a Linux system. If you wanted to install a third-party package, you went and downloaded the source code, compiled it yourself, and then it copied the programs into the correct directories. And then when a new version came out, you followed that process over again. You download the latest one, compile it, and install it. Because like I said, there weren't package managers. Now, you don't just say update, and then it does it. And there are still some people that prefer to do it that way. They don't trust the pre-compiled packages that the manufacturers or the distribution makers build. Like, who knows if somebody has snuck in some extra code to, copy your password file.
Yeah, there's a lot of things that I download that's me.
So they want to build it from source every single time.
Yeah. It's small stuff usually, but you can back when I was playing World of Warcraft, you can download on the Curse Forge Manager, you can download an add-on and then just have Curse install it on your computer for you.
Yeah.
I was like, I know how to do it, so we're not going to do that.
You'll probably notice that whenever we run a program, we go /a.out, right, or crack. And the reason why we put that / on the front is because the shell does not by default look in your current directory for executables. It looks in the system directories, right? It looks in the /bin directory and the /user/bin directory, but it doesn't look in the current directory.
That's why.
So that's why we have to put that on there to tell it to look in the current directory for this executable. We're telling it this is where it is. It's here in the current directory. If it was in a different directory, we could actually put the full path on there, right? And then it'll work. What was I going to say? Oh, but when I was first learning to use a Unix system, it did look in the current directory by default. And in fact, that's all controlled by a variable called the path variable. This contains a list of the directories that it's going to look in for programs. And the default back then, 30 years ago, was to include dot in that list. So up here at the front, it looks in order, so it looks in this one first, then it looks in this one, then it looks in this one, then this one, then this one, this one. So it looks in order, and so the default was to also include dot in this list. So that I didn't have to...
Can you change that?
Yeah.
Like currently?
Yeah, I can go export path equals dot colon, and then let me just paste in the previous value. Okay, and now I can just type in. Well, it's running, right? But it's let me go over here. Let me pop back over to here and do the same thing that I just did.
And every time you load it, you would just change that path definition.
Yeah. Mm-hmm. Or you could put it in your startup script. There's a script that runs whenever you log in, called the .profile or the .bashrc file, and you just put that line down at the bottom.
I might do that.
So now if I type in, now I don't have to go ./crackword. I can just say crackword, right? And it runs it.
That's neat.
Okay. But the reason why the dot was taken out by default was because of shenanigans that people like me were doing back then, which was, well, let's just create a script called ls. Now when I type in ls, it actually does the command and then it goes, haha, got you, right?
Right.
You know? And so then what you do, if you're, really nefarious, is you go like this.
Oh, I never even thought of that. Yeah.
So you type in ls and then boom, all your files are gone.
Wow.
So what would happen is you're in the computer lab, right? And someone goes off to the bathroom. And so very quickly you go over to their computer, you type this in, save it,
and hope they backed everything up.
And then when they come back from the bathroom, they go ls, and then boom, all their files are gone.
Wow.
So as a result of that, dot is no longer included.
Yeah.
In the default path, so that you can't. I mean, you could still do this. Obviously, I just did it, right? But you have to go out of your way. I better remove that.
Yeah. Wow. Oh, I would be so angry.
And of course, in the process of removing everything, it also just removed all traces of itself.
Yeah.
So, you didn't know what just happened.
Yep. Yeah, right? Yeah.
might just leave the lab at that point, right?
Walk out before something bad happens.
You the prankster or you the victim?
Both. Oh, boy.
Yeah, so that's why dot is no longer included. So you can't pull that off as easily now. I mean, you still could if someone's gone long enough. You could go and change their path and put that script in there, and but it's just harder now.
Yeah. Oh boy.
That made a lot of us very paranoid all the time.
Yeah, I bet.
We would go which ls and just make sure it like was the correct one.
Yeah.
You know, if it came back and said ./ls, we'd know, okay, someone has just stuck a command in there.
Yeah.
And then, you know, you don't even have to put in commands. You can do stuff like create shell aliases. You can go alias, alias, ls equals remove, right? So when I type ls, it actually removes.
Yeah. Oh man. And everything's gone.
Yeah. Oh, fun times. Well, I mean, that's how I did a lot of my learning, right?
Yeah.
Was like, well, how does that work, right?
Playing pranks on people?
Well,
he delays.
I didn't do it. Was my buddies that did the prank. Really, honestly.
Oh, sure.
Right? But someone was like, hey, can you do this? I'm like, how does that work?
Yeah.
You know.
That's funny.
And you used to be able to use there was a program called Write. And what you could do is you could, I think what you did, well, first of all, you did something like, you know, who to find out who's on the system. Now, these are virtual machines, so there's no one else on the system, right? But there used to be these giant multi-user systems, actually like our regular server is. Type in who, you can find out who it is, who's on there. And then you could type write and the name of the user and then a message, and that would appear on their terminal. It would actually like send that command to their terminal, not the command, that text. And so this was a rudimentary way for us to start chatting with each other.
Right? And write's gone. They've taken it away.
Well, so if you have given permission for other people to write to your teletype, right? So it used to be that the permissions were read, write, read, write, read, write. So anyone could write to your terminal. And like I said, that's how we started chatting with each other, right? We just pick a random name out of the list and just start chatting with them.
That's funny.
And then, so now the default is just read write for the user and no permissions for anyone else. If you turn that back on, then you can start using that command to send messages to each other.
A little too powerful, though, since it just interrupts whatever anyone's doing on their own terminal, right?
I mean, it interrupts in the sense that the message appears, but it doesn't. Remember, the standard input and standard output are two separate data streams. So if something appears on their standard output, it doesn't interrupt their standard input. So if they're in the middle of typing in like a compile command, they just keep typing it in as though nothing happened. It's just something that appeared on your screen. Now, what we might do back then is we would log in twice. We would log in with one that had the write permissions turned off so we could do our work, and another one that had write permissions turned on so people can come and chat with us.
How does that work?
Logging in twice?
Yeah.
Like open two windows?
Oh, I thought you didn't have a window.
Oh, back then what we would do is we would use a program called Screen.
Oh yeah, I've heard of Screen, yeah.
That allows us to run like multiple virtual terminals on one terminal, and then we can flip back and forth between them. By the time we learned about Screen, though, we had learned about the command called talk, which actually did more like a real-time chat thing, where it split your screen in half with a line, and on top was your stuff, and the bottom was their stuff, and they could see you as you were typing. Right? So the embarrassing part was that you learned like who was a fast typer and who was a slow typer.
Yep.
So some people would not use that because they're like, oh man, my typing skills are not that good.
Hunt and peck, hunt and peck.
Yeah. And then the nice thing about talk also is it worked over the internet.
Oh, that's
cool. So if you could get someone's username on another machine, you just basically said talk and then their email address, like username at machine name, and then it would make a connection over the internet to them. And so that's when we really started like chatting with people that were just out there. Like we would like find a internet posting from someone and just randomly like talk and then their email address and to see if it worked. And then start chatting with them.
That would be creepy.
Kind of like chat roulette, right? Where you just pick someone.
if you're that guy on the other end doing your work and it pops up, somebody's chatting with you, it'd be like, what?
But again, you could
What
turn that
is
off.
this?
If you didn't want to be
Yeah.
bothered, you could just turn that off.
Yeah. I've seen too many of those movies. Somebody takes over your computer and
John says,
was that
friends in high school would copy and paste thousands of lines of ha ha and send it to your phone as a text message, I guess. And it would just constantly render your phone useless because it was just receiving all these lines of text.
Tragedy of Darth Plagues the Wise? No.
While the punchline's being typed in here. Someone says, what's the next lessons we're doing? Oh, so next week we're working on making the crack program faster by loading the dictionary into memory and building a data structure so we can search it efficiently. That'll be next week and possibly part of the week after that. And then after that, we're on to networking. We're learning how to write programs to send messages back and forth to each other. One of the projects we did in the past, and may resurrect it, is we did a chat program so that two people could be running their chat program simultaneously and send messages back and forth to each other. More common one that I do is a file downloader. That way you don't rely on someone else being online at the same time. You would just talk to a server, you would fetch a file, and it downloads it to your computer. I'll have to look it up, Ben.
I know, that's what got me. Oh, I have a quick question.
Yeah.
So I'm finally getting caught up a little bit. I've got getting caught up more on assignments, and for submitting the like Lab 7 and 8 that are through the Git stuff. I mean, it sounds like all of them are going to be from here on out, but for those ones, all we have to do is send you that link.
Yep.
Okay, cool. Because I know for 6 we had to like email and share it to you. Sounds
you
like
still have
it's
to
easier.
share it with me.
Okay, I have to do that. Okay,
Yeah,
I will still.
yeah.
I'll go do that then. I didn't do that because I wasn't sure.
Yeah, you still have to share it with me, but you just send the URL.
Okay, cool.
Any other questions? Are we done?
a quick question about another class, just kind of off topic?
Mm-hmm.
Because you taught 50, right?
Yeah.
So I was thinking of doing that final project as the a push file that creates a table and kind of organizes everything in that table, so you could just pull it up and see without logging on to the website, see what's been pushed, the date that it was pushed, what comments were on it, all of that stuff. Is that it's starting to feel like that's a big project.
So it would like query
It would
Bitbucket or something?
No, it would. You would use the shell to push your stuff, but you would use the command to run the shell script that would then run all the commands that are needed to send that stuff off. To add it, commit it, add the comment to it, right? And you would do that. It would prompt you, and you would type all that stuff in, and then send it over. And it's essentially doing the same thing, but we have to create a final project. And I got the example project that he put out, and it was like, enter in the grades and then add the grades up and get the average and then display it in a HTML package. And so I'm like, I think this might be too much, but I don't know. I haven't started putting it together yet. So it doesn't.
Yours is just simply to prompt the user for the information and then run the commands. That's easy. That's probably within the scope. If you want something like, you also have to incorporate a database, or you have to incorporate a web page.
Yeah, I'll use SQL to populate the database.
I think
that's
it's okay.
Okay, cool. I guess if you were teaching it and somebody said, "Hey, I'm going to do this," and I'm doing it by myself, so I don't have any help with anybody. There's some people grouping up, but my schedule's too crazy.
I think that's okay.
Okay, good. Cool. He has a hard time of getting back to me with questions, so.
Well, people on YouTube are wondering who I'm talking to. These are my Zoom students. So it's not a Discord, it's a Zoom. All right, I think we're done for today. We'll be back, see, today's Thursday, right? So we'll be back next week.
Yep. Sounds good. Enjoy your weekend. You do anything for Halloween?
Oh yeah, the kids are going out.
Trick-or-treating?
Yep.
Yeah.
We got a trunk or treat tomorrow.
Oh, nice.
There was
Those are always fun. Yeah. Lots of candy. I feel bad.
I think my son has forgotten about the bag he got from trunk or treat.
Oh yeah.
One of my friend's dads says like, okay, they go out trick or treating, they get their bag of candy, and then like, you know, of course you have to like put it in a jar, right? They can pull out one candy a day. But meanwhile, the parents are pulling out multiple pieces and just putting it right in the trash.
Yeah.
So it doesn't last as long.
Yep. Yeah, I wonder if that's what my parents did, because I was thinking back on it and I'm like, man, I would get pillowcases full of candy and I'd find stashes. And if I stashed it myself, it lasted forever. But if I didn't, it always went fast. And I just assumed people were eating it.
They might have been,
yeah,
or they might have just been.
No, I'm sure that was a lot of candy to eat. I'm sure they were throwing it away. It makes sense now.
As a parent, you're like,
I know, right?
You know, pro parenting tips. Right?
Yep. I know. I want to do that. I don't know. I'm still debating it. Have you seen those YouTube videos where the mom's like, I'm really sorry, or the dad's like, I'm really sorry, I ate all of your Halloween candy? Have you seen those?
No.
Oh, you should look it up. And the kids just go berserk. They get so mad and they're like, no, I'm just kidding. I'm just kidding.
Oh yeah, I've seen those.
Oh, it's so funny. The kids get so mad. Some of them like will start to cry and then it's kind of sad, but others just like start throwing stuff around and all mad and kicking chairs over and like, oh boy. Pretty funny.
Check those out.
Yeah, they're pretty cute. A lot of funny stuff on there. The kid that loses, he was playing something competitively with another kid, computer side by side, and they were super into it, trying to beat each other, and the one kid loses and he gets so mad and he grabs his keyboard and he rips his keyboard off and the cord comes out, he's all wham, and hits the other kid with his keyboard. That's a pretty funny video too.
All right. Indeed. Have a good weekend.
You as well.
Yeah.
See you Tuesday.
Yep. Have a good Halloween.
You too. Thanks.
Happy Halloween.
All right.
Happy Halloween.
Bye-bye.
Bye.
See you guys.
Recording stopped.
And then the YouTube folks who are left, like I said a few minutes ago, next week we're going to continue doing the hashing programs and then work on making them faster, because once you put in the dictionary with 1 million words in it, it starts to slow down a bit. And then after that, it's networking, and there might be some days towards the end of the semester. We still got, let me think, about 6 weeks left in the semester. So we might, 6? Maybe 5. So we might have some time towards the end where we kind of have nothing scheduled, and then we can do some extra stuff. We'll figure out what that is. So it's all good. Well, have a good weekend, everybody. We'll be back on Monday for my discrete structures class, and then Tuesday for my C programming class again. Have a good one, everyone. Bye-bye. Have a great day.